Yeah, no, erase it. Hi, I'm Mike.
I'm other Mike.
We're going to do the crazy Henderson Hasselbalch equation for you from exam 1. We'll use question 2 as our example. We divide this problem into 2 parts. Part number 1, we take the basic information given. We have 240 milliliters of 0.5 molar peptide, which is at a pH of 4 to begin with. We figured that is 0.12 moles. After quantifying that, we set up an ice equation. The ice equation has all different protonated forms of equilibrium, and then given in the problem are pKa's of each equilibrium in each step along the way, 1.2, 3.4, 6.8, and 10.1. You can follow along in the exam that you probably still have and have cried over. The Henderson-Hasselbalch equation, laid out in generic form, is the pH equals the pKa of whatever equilibrium you are at, plus the log of the conjugate base over the protonated acid. We'll use this one time simply to figure out where to start. We know from our problem that we start with a pH of 4. We just figured out that 4 is closest to 3.4, and this is our equilibrium here, so we'll use this pKa, 3.4, plus the log of the conjugate base over the protonated acid. Let's do a little bit of algebra. 4 minus 3.4 is 0.6, therefore equals the log of the conjugate base over the protonated acid. 3.98 is our answer. That's pretty close to 4. We have a 4-to-1 ratio of conjugate base to protonated acid in our equilibrium. That's a pretty good starting spot. Next, we're going to throw a monkey wrench into the whole thing. The problem then asks us to add 50 milliliters of single molar hydroxide. 50 milliliters of single molar means that we have 50 millimoles of hydroxide to add into our equation. I'm going to turn it over to Mike for the second part of our problem.
All right. So, from this 4-to-1 ratio of the 120 millimoles of peptide UNCA that we have, we can figure out algebraically that that ends up to being 96 millimoles of the conjugate base with 24 millimoles of the protonated acid. So we'll plug this into our ice chart here, and that will lead us to 96 and 24. So now we come back to the 50 millimoles of the hydroxide added. It's actually base, not acid. I don't know why I said that. So we know first off it attacks the most easily ionizable group, which is the 24 millimoles of protonated acid. So subtract out the 24 millimoles that is used of the hydroxide to attack, leaving us with 26 millimoles left, which completely eradicates that ionized form. Now, as this is an equilibrium, we have to remember that since this is protonated, deprotonated, we have to add it to the conjugate base, which leaves us with all of peptide UNCA in that ionized form. Now, to further react the rest of the hydroxide that was added into the solution, we then further deprotonated this with the 26 millimoles of hydroxide that was left, leaving us with 94 millimoles. So, as we did with the deprotonation and equilibrium here, we also have to deal with this. So, as this ionized group originally had no millimoles in it, we now have to add in the new conjugate base of the 26 millimoles here, which leaves us with our new equilibrium. So we can then further plug that into the Henderson-Hasselbalch equation here, as with our new equilibrium, we have a new pKa to go along with it that we have to remember to use. 6.8 plus the log of our new system in equilibrium, which is 26 millimoles of our conjugated base here, and 94 millimoles of our protonated acid, which, as you plug and chug into the equation, you'll find to be that it is pH equals 6.8 plus negative, because the log of less than 1, 0.54 or
0.56.
0.56, I can never quite remember. Which brings us to have our pH equal 6.24, and that is the final pH of our system.
Pretty crazy, huh?
Yeah.